Hello, and welcome to Empowered Learning. This particular video will be about factoring trinomials. And so we'll talk about how to factor via trial and error, as well as factor by grouping. And so we'll also get into some special cases where we do the factoring via the square root method, as well as studying the difference of two squares, the sum of two cubes, and the difference of two cubes as well. And so this particular skill is needed so that when you get into solving, for instance, quadratic equations, you'll have the tools to be able to factor, to easily figure out what the x-intercepts are whenever you solve those type of equations. All right, so let's go ahead and get started here. So we're going to begin with some vocabulary, just to make sure that you're familiar with some of the nomenclature that goes along with factoring trinomials. So the first thing that we want to talk about is an expression that has exactly three terms. So an expression that has exactly three terms is called a trinomial, okay? Hence the title of this particular video. And so factoring trinomials are most often done by the following two methods. And so we'll talk about trial and error, as well as factor by grouping. And so for an expression ax squared plus bx plus c, it might be best to factor via trial and error if the coefficient is equal to 1. In other words, if we have something that looks like this, x squared plus bx plus c. And an example of what you may get as a trinomial type of expression will be something like this. Let's get rid of that. So something like this, okay? Now, if our leading coefficient, which is what a is, if it's not 1, then it might be best to use factor by grouping, depending upon how big the numbers are, okay? And so now I have the suggestion here that especially if a is a number that's larger than 10, okay? And so again, a is called the leading coefficient. And the coefficient is just a number next to a variable. All right, so for the trial and error method, the way that we want to go about trying to factor these particular trinomials is we want to take into account the things that have to happen, okay? But before we get into that, I kind of want to take a step back here to just talk about what do we mean when we're actually factoring. And so we're going to, let's say we take it back and we just want to figure out what the factors of a certain number are, okay? So let's say we take the number 15. We know that 15, if we do a factor tree, will be 3 times 5, okay? So in the sense of the world of polynomials, and in particular these trinomials here, what we are doing is we're saying we have some expression and we want to break it down into its factors. So if you were taking the expression, let's say two binomials, and you were multiplying them together to be a trinomial, if you recall, most people do that via the FOIL method, and that would be the actual multiplication of those expressions to get the product right here, okay? So essentially, I'm saying all this to say that when we do factoring, we're actually doing the FOIL method in reverse, okay? And so since we're doing the FOIL method in reverse, and FOIL just means we're multiplying the first terms together, outer terms, inner terms, and last terms, in case you have forgotten. So we're doing the FOIL method in reverse, and because of that, we know that there are certain things that have to be true when we factor. And so that is what these items down here are all about. So when we have our leading coefficient being 1, and we see here that our signage is such that we have two addition signs, so plus plus, we know that the way that it's going to have to factor out is going to be x plus something times x plus something else. When we have plus minus or minus minus, then in both of these cases, one of our factors is going to have an addition sign, the other one's going to have a subtraction sign, okay? And then of course for the last one, if we have minus plus in this order, then we know that both factors will have a subtraction sign in it, okay? And so when we do trial and error method, we start off by noting that, and then from there, we do the best that we can to take what C is, whatever number that is, and we'll say what times what is equal to C. And so we'll just stick those factors in these two spaces, and then we apply the FOIL method to both the outer and the inner terms to make sure that what it is we came up with is correct. Sometimes, depending on where you place the factors, you may not get the correct answer. And so in that sense, you can switch them around or use two different factors altogether to see if that works. And so hence why this is called the trial and error method. Okay, so we'll go ahead and move on here and see some examples. So our first example here, we see we have x squared minus 3x minus 10. Okay, and so we see first off that our signage is such that we have minus minus here. So minus minus. So therefore we know that we're going to have x plus a number and x minus a number. Okay. So now from there we look at what are all the factors of 10. Well, we know that plus or minus 1 times plus or minus 10 is 10. And we know that 2 times 5 is 10. And so I'm just adding the plus or minus because we know that a negative times a negative is a positive. Okay. So if we look here, we see that the correct factors to use are going to be a 2 and a negative 5. And so the reason for that is we're looking for the factors of 10. So we're looking for what times what is 10 that also adds up to be a negative 3. Okay. And if we look at all those situations here, we see that if we took 2 and added it to negative 5, the result would be a negative 3. Okay. And so that's what I'm trying to show here and here. We know that 2 times a negative 5 is a negative 10, but 2 plus a negative 5 gives us a negative 3. So we see that those two factors should be the ones that work. So now what we have to do is make sure that we put them in the right place. And so you see that I put the 2 in the first place and the 5 in the second one. Okay. And so how we check all that is that we could multiply the inner terms and the outer terms to see if they actually add up to be negative 3x. Okay. So, and again, so the outer and the inner terms have to add up to be whatever this is right here. So if we do x times a negative 5, that's going to be negative 5x. And if we do 2 times x, that's plus 2x. And of course, that turns out to be a negative 3x. Now, the reason why we don't worry about doing the f and the l, meaning multiplying the first terms here and the last terms of the FOIL method, is because based upon our setup, we have to have the first term and the last term be correct. If you notice here, if we do x times x, that is x squared. And if we do 2 times a negative 5, that is a negative 10. So if we do our signage correct and put x in the first term in each factor, then we don't have to worry about that because it'll always be the same. Okay, it'll always be correct. Now, the note that I have here is if we place the 5 next to the subtraction sign, to make it -5, because the coefficient is a -3 here, had to be negative, okay? So basically what I'm trying to say is this. I have this note here, but what I really want to talk about is the following. Let's say we switch these, okay? So let's say we had x plus, have x minus, and let's say instead of putting the 2 here and the 5 there, we put the 5 there and the 2 here, okay? So if we did that, if we multiplied all the outer and the inner of the FOIL method, we would have -2x plus 5x, which will give us a positive 3x, okay? So here you notice that 3x or positive 3x is not the same as negative 3x. And so in knowing that, we know that this would be the improper order. And so that's why we would have to come here and say, nope, I want the 2 to be here, and nope, I want the 5 to be there, okay? So whenever you're doing the trial and error method, sometimes you may not place it right, but again, you can always switch it around to see what works. All right, so let's move on to our next example. So now we have x squared minus 11x plus 10. And of course, you see here with the signage, notice that we have minus plus in that order. So that means both factors have to have a subtraction sign. Okay, and so now we're asking ourselves, what times what is 10 that also adds to be -11? Okay, and so you can see from the choices that we have here, if we picked a -1 times a -10, of course, that would give us a positive 10, okay? And so that's exactly what I'm saying here. But if we took -1 and added it to -10, we would have a -11. So those are the factors that we want to pick. And so from there, we just place them. And since we have subtraction signs for both, it really does not matter where we place the 10 and where we place the 1. So here we put 1 and 10 in either one of these spots. And of course, if we multiply this out, we'll have minus 10x minus 1x, which gives us a minus 11x, which is what we need. So we know that x minus 1 times x minus 10 is the proper factorization for this particular trinomial. Okay. All right. So with that, you could read this note here. I'm not going to mention too much about it, but you could read it. So pretty much everything that we've already talked about has been said here. So I'll just give you a second to read that, and then we will move on. Okay, so if we move forward here, I want to make a note about this particular connection note that I have here. And it says, note that when we factor a trinomial like the one that we just got through working on, we are doing a process very similar to taking a number, say 21, and rewriting it, okay? So basically what I'm trying to reiterate here is the same example that I did when I was talking about 15, how we break this down to 3 times 5. So again, I'm trying to make sure that we understand that when we do this whole process of breaking down a number, or the proper way to say it is factoring a natural number into its unique prime factorization, we're doing the same kind of thing here with trinomial expressions, okay? All right, so with that, we are going to do a series of examples just to kind of get us going here, to get a feel for how this works. All right, so for this first example, we have this quadratic expression here, or this trinomial rather, and here we know from the beginnings we have plus, plus, and our leading coefficient here is an understood 1, so we have x, x. And so now we look at 4 and we say what times what is 4, but also adds to be 2. And if we think about that, we know 2 times 2 is 4, but 2 plus 2 is also 4. So here that means we could put 2's here, and if we check what we're doing here, that'll be 2x plus 2x, which equals to 4x, which is the same thing that we have here. So we know that this works. So our answer for this is going to be x plus 2 times x plus 2, which we could write as x plus 2 quantity squared for short. For the next example, we notice here that we have minus plus, so that means we have minus, minus, and of course we have x, x. And so now we ask ourselves, what times what is 40? But when we add it, it's going to be a negative 13, okay? So we know for 40, we have 1 times 40, got 2 times 20. We also have 4 times 10, and we have 5 times 8. And of course, the 5 and the 8 would work if we made both of these negative. We know that a negative times a negative is a positive, and so that would give us a positive 40, and a negative 5 plus a negative 8 will give us a negative 13. So here we just put the 8 and the 5 and the 8 there. We'll check it just to be sure. Negative 8x minus 5x gives us a negative 13x, which is exactly what we want here. So we know that our answer will indeed be x minus 5 times x minus 8. Moving on to our next two examples. Here we see that we have minus, minus. So when we do our factoring here, where one's going to be minus, one's going to be plus. So x, x. And so now we ask ourselves, what times what is 24? Well, negative 24 rather. That adds to be a negative 2. Okay. So if we start running through the factors of 24, we'll notice that 2 times 12 is 24, but we want this to be a negative 24. So if we made the 12 negative and the 2 positive, then that should work, because we know that positive 2 times negative 12 is a negative 24, and we know that 2 minus 12 is a, oh, sorry, that would be the other way. Yep, I was thinking that that was something different. So let me erase that. Yep, so that would give us a negative 10, and that's not what we want. Okay, so actually the factors that would work would be 4 and 6. Yeah, that would actually be the ones that would work. So here, since we have to end up having a negative number here, if we had a negative 6, positive 2, then we see that that would work, because a positive 4 times a negative 6 is a negative 24. But also, if we added these two, so 4 minus 6, that would give us a negative 2. And so I hope you noticed how I was thinking that one of the pairs of factors would work, and you saw how I caught myself in that mistake. And so normally if you go through the questions that I'm saying, you'll see that, hey, even if you think something is right, when you actually go through the series of questions of trying to make it all work, a lot of times you'll catch your mistake before you actually get to the point of plugging in the numbers. All right, so we figured out that these two factors should work. So since the 4 is positive, we need to put it there. And since the 6 is negative, we need to put it there. And of course, we can check just to be sure. X times a negative 6 is a negative 6x. And 4 times, positive 4 times x is a plus 4x, which gives us a negative 2x, which is what we want here. So indeed, our answer is just x plus 4 times x minus 6. All right. So moving on to the next example. Here we have plus, minus. So just like minus, minus, one of these has to be plus and one of these has to be minus. So I'll redraw that to make that look a little better. And so of course we need to have x here, x there. And so now we're asking ourselves what times what gives us a negative 72, but adds up to be a positive 1. If you think about your multiplication tables, you know that 8 times 9 is 72, but we need a negative 72. So one of these factors has to be negative. Since the result here has to be positive, we want to allow the bigger factor to be positive. So if we let this be a negative 8, positive 9, like that, then if we multiply those, we get the negative 72. But when we add negative 8 plus 9, that gives us a positive 1. Okay, so what that tells us is that the 8 needs to be here, the 9 needs to be here. And when we check this out, doing the outer and the inner part of the FOIL method, we see that we'll have negative 8x plus 9x, which gives us a positive 1x, which is just x, which is exactly what we have here. So therefore, we know that x plus 9 minus x minus 8 is indeed our answer. Okay. All right, so for our next example here, we see that we have minus, minus again. So we have minus, 1 plus, and we have x here, x there. And so now we have to think about what times what will be a negative 91, but add to be a negative 6. And of course, if you're thinking about this, you may not necessarily remember right offhand what times what is 91. So acting as if you don't remember that, one thing that you can do to sort of try to help you out is to remember, okay, what times what has the first digit of a 1, okay? And so one of the things that comes to mind, of course, 1 times 1. But the next thing that comes to mind is, what about 3 times 7? Because 3 times 7 is 21, okay? Now, of course, that means that somewhere in whatever you're doing here, when you multiply it, you're going to have a 3 and a 7. So my guess here is that, what about 13 times 7? Okay, if I do that, I would have 1 here, carry the 2, and 7 times 1 is 7, plus 2 is 91. So that ends up working for us. Okay, so here we know that the factors are going to be a 13 and a 7. So now we have to figure out which one is going to be positive, which one is going to be negative, because we see that our term for C here, and what I mean by C is if we're doing ax squared plus bx plus c, where this a here is understood to be 1, then c is this term here, and so that's what the minus 91 is right there. So we know that the result in the middle has to be negative, so that means the bigger factor has to be negative. So we're going to put the negative on 13, positive on the 7. So here we'll put 13 here, put the 7 there, and then from there just test it out just to make sure everything works. So I'm going to get rid of this last expression down here at the bottom. Okay, so now we'll test this out just to make sure everything works. So we have a positive 7x minus 13x, and I really shouldn't put that positive like that and just leave it as that. And that would be a negative 6x. And so we know from that x minus 13 times x plus 7 is indeed what this particular expression factors out to be. Okay, so now we're going to get into factor by grouping. And so what I'm about to show you now is just from a theoretical standpoint how we actually come up with the whole concept of factoring by grouping, and the process, because there's a process to it, and I want you to be able to see why and how that process is what it is. Okay, so we start off by just considering that we have two binomials that we are factoring together, multiplying together. And if we multiply those via the FOIL method, this is what it comes out to be. And remember, for the FOIL method, we have first terms, and then we have outer terms, then we have inner terms, and then we have last terms. Okay. For those of you that do not multiply via the FOIL method way, and you do it, let's say via vertical stack method or box method, you'll be able to still see the same thing whenever you multiply it out that way. Okay. So once we multiply it out, the main thing that I want you to see here is this, is that you notice that your coefficient for the first term is A times C, coefficient for the last term is B times D. And if you notice here, the middle term is both of these coefficients here. It seems like they're kind of mixed together here. But if you notice, we have this AD plus BC. Okay. Now, if we look here, it says, so if we let A equal AC and C equal this and B equal that, then this will be some kind of quadratic expression here. Okay. Now, I go a little bit deeper to show you why this is what it is. Okay. And so we say, note here that if A and C, which are the A and C that are here, are 1, then this simplifies to this case here, and thus we're really dealing with the case of what we just got through talking about, which is whenever we have a leading coefficient of 1, how we would actually do the factoring. And so if you notice, we always asked ourselves, what times what will give me this number, to where that plus that same the factors, if we added the factors together, it would be this middle number here. Okay, so I'm showing you via a theoretical kind of way of how we were actually doing the factoring via trial and error. Okay, so notice that for C, B, and D are the factors, and of course for the number B that's right here, we know that if we add those factors together, that would be that middle number. So I'm just trying to make that connection. So if we take that same way of thinking and go into our note 2 here, if you notice that if we were to multiply the first terms and the last terms together, then we would get this AC times BD. And of course, since multiplication is commutative, I could switch around these factors in such a way to where now I have AD times BC. Okay. So in other words, I move the D over here to the C where the C is, and I move the C where the D is, right there. So if I do that, I end up having this. And then if I apply the associative property, then now I can say AD times BC. Okay. And so if I have that, then here you notice that I still have that same mix of stuff right there with the AD plus BC. Okay. So whenever we multiply these, my whole point in saying that is that we're really doing the same thing as we did when we worked with the trial and error method, which was what what times what for the factor C will also add up when we use those factors to be the middle number B. And if you look at it in terms of the case where we have a leading coefficient 1, we're still kind of doing the same thing. Because instead of just having some non-zero coefficient for A, we just have, sorry, not non-zero. Instead of having a 1 for the first coefficient or the leading coefficient, we have something that's not equal to 1. And so that's why this ends up looking this way. If it were equal to 1 and we did the same exact thing, you see here that how we have just 1 times BD, and of course, we still end up with the same thing that we were talking about up here. So saying all this to say is that we start off when we do factor by grouping by multiplying the leading coefficient and the last coefficient. And I just express that as the first and the third coefficients. Okay, so if we multiply that and then break down that number into some type of factored form, into its factors, to where B times D is that result, but B plus D, or in this case, AD plus BC, ends up being the number that we need in the middle there. Okay, so just saying all that to let you know that what we're about to do kind of falls in line with what we have been doing. It's just that we haven't revealed the whole truth to it yet. Okay, all right, so in short, here's the strategy that we are about to employ when we do factor by grouping. I'm just going to read through these and then actually practice it through example here. So number 1, we multiply the first and last coefficients in the trinomial. Okay, so you just saw me go through that sort of theoretically. Number 2, we find the factors of the result from number 1, which we just stated, that will yield the second coefficient if you added or subtracted these factors together. Okay, so what I'm talking about here is if we know that we have AD times BC, then we want to figure out, all right, well, what are we going to have to split this up into so that if we have, let's see, AC plus BD, that ends up, giving us the number that's in the middle, or that coefficient B there. Okay. So for number 3, we need, and here's the key. Once we figure all that out, we're going to rewrite the trinomial's second coefficient in terms of the sum and or difference of the two factors found in this step. So in other words, we're finding the factors of AD times BC so that we can rewrite the two middle terms in terms of these two factors here. Okay. And then after we do that, our next step is to group the 4 terms that we will have now into 2's, and then factor out the greatest common factor in each term. Okay, and then we just keep doing that until we get an answer. And that's essentially what the process is. And so I'm going to show an example here before we do some, just to kind of give you an idea of what this looks like. Okay, so let's factor 12x squared minus 23x plus 10. And if you look at this, we start off by just multiplying the 12 times the 10. And what we're really doing, to have full disclosure of this, we're really multiplying the first 2 whole entire terms. And if we do that, we get a positive 120x squared. And so saying all that to say that here, when we have to do the step of rewriting this in terms of 2 other terms, we are thinking as if we have x's by all of these, okay? Because of course the x part has to be in there. So just want to make sure that we're aware of that. When I wrote this, I did it in such a way to where we can just focus on the numbers, because again, we can just easily just plug in the x's there. All right, so when we figure out that, hey, we have 120 and we list all the corresponding factors, we're looking for the factors that add up to be a positive one, well, multiply to be a positive 120, but add up to be a negative 23. And if you notice, this is the one that works. In other words, negative 8 and negative 15. They add up to be a negative 23, but when you multiply them, it's a positive 120. So that's what we're showing here. Now, from that, what that means is we want to replace this particular term here with negative 8x minus 15x. Okay? And so that's what I'm actually showing here. And so one extra step that I do right here, just to make sure that I don't mess up the signage of anything before I start doing my factoring, is I change all of my subtraction signs to plus a negative using the definition of subtraction. Okay. And so some of you may not need to do this. I know for me, I do. So that's why I do that, just to make sure that I have no issues when it comes to signs. So from that point, I look here and I say, all right, I'm going to group the first two terms together and the second two terms together. And you see I've done that, and then I factor out the greatest common factor in between each group. And so the idea here is that whenever you do this, if you're doing factor by grouping, what you get inside of parentheses should be the same. Okay. If you find that you get something that's not the same, either you've made a mistake or you won't be able to factor out the particular expression that you're working with by using factor by grouping. And usually what this indicates is that you have some irrational or complex type numbers that you need to be able to multiply that out. To factor it out. Okay. So anyway, so we're here. If we look at our first two terms here, we see that the greatest common factor is a 4x. So we factor that out. We have 3x left in the first term and a negative 2 left in the second term. And then for the second group here, we see that our greatest common factor is a negative 5. And of course, I chose negative 5 because if you notice here, let me get rid of that. If you notice here, I have a 3x minus 2. And so I have a addition sign there, and I need to have a minus sign there because I want this to appear the same way that this does. So I need a minus sign. So to do that, I'm going to have to factor a negative out of one of the factors of 10. And so I'm looking at 10 in this case as a negative 5 times a negative 2. And so if I factor out the negative 5 in this term, a negative 2 is left. And if I factor out a negative 5 out of this first term here, then we see that we have a positive 3x left. So you see, we essentially get the same thing. So from that, when we factor out everything, we see that we have the 3x minus 2. 3x minus 2 is the same. So now we go and factor that out of both terms, and we write what's left. So in the first term, what's left is a 4x. What's left in the second term is a negative 5. And so if we use the definition of subtraction again, we just write 4x plus a negative 5 as 4x minus 5. And so this is what this will factor into. Now, this seems a little longer than the trial and error method, but the thing that you have to remember here is that we just do the thinking up front, and then everything else is following the process, okay? Whereas with the trial and error method, we have to do a whole lot of thinking along the whole way. So we have to do a lot of this trying stuff out. And so not as much as being written whenever you're doing the trial and error method, but you do have more written whenever we're doing the factor by grouping. Okay. All right, so we know that now this particular expression here, this particular expression is can be factored into 3x minus 2 times 4x minus 5. All right, so now we'll go to this next example. Now, this next example is a great example, in my opinion, of how factor by grouping could be used if the numbers are relatively big. And so I'm not going to go deep into it. I'm just going to show you that, hey, if we know how to factor out the number that we get whenever we multiply the first and last coefficients together, that this allows us to have a very systematic way of doing it without having to think, all right, well, what times what is 3,780, okay? Now, again, this could be done via the trial and error method as well, but you would have to try out a whole bunch of different scenarios with that to see which one works, okay? And so you may like that, you may not. So it just depends upon how fast you can think. All right, so for this example here, we multiply the first and last coefficients, and we see we get 3,780, and then we find out all the factors of 3,780. So I have them listed here, and we see that the ones that work will be 60 and 63, okay? And because we know 60 plus 63 is 123, but 60 times 63 will be the 3,780. And so we take that, and from here, we rewrite 123x as 60x plus 63x. So we write that, group the first two terms, group the last two terms, and then factor out the greatest common factor for each. And so for the first two terms, factor out a 6x, and for the last two terms, factor out a 7. And if you notice, they have a 9x plus 10 inside the parenthesis for both of them. And so from here, we factor out 9x plus 10, and we have 6x left in the first term and a 7 left in the second. So we see that our particular expression here just factors to be 9x plus 10 times 6x plus 7. All right, so the last thing that I want to mention for situations like this is that I understand that for the number 3,780, that it has a lot of factors, and you may not be able to remember or even know what all the factors are. So one thing that you can do is you could use a factor tree and have that factor tree help you to be able to figure out what the factors are. And so I'll give you an example of what I mean by that. I won't go through the whole list, but I'll kind of give you an example of how I actually figured out all those factors. So if we use a factor tree, we know that 3,780 is going to be 54 times 7, because that was kind of what was given to us. Now, if we break down 54 into its factors, we see that 54 is 6 times 9, and then of course 6 is 2 times 3, 9 is 3 times 3. We do the same thing with 70. 70 is 7 times 10, and 10 is 2 times 5. So we want to break everything down into what we call this product of prime numbers, okay? So from there, we notice that we know that we're going to have 3,780 is going to be 2 times something. It's also going to be 3 times something. We know that since we have a 2 right here and a 2 right here, it's also going to be 4 times something. Since we have a 5, it's going to be 5 times something. We have a 2 and a 3 here, so we know it's going to be 6 times something. We have a factor of 7 here, so if we move forward here, it's also going to be 7 times something, and then so on and so forth. Now, we say 2 times what? So let's say we use this 2 here, okay? So 2 times, well, all we can do now I said what we have to do now is just multiply 2 times everything else. Okay. Now, of course, in this instance, it may be easier for you to just take this and divide it by 2. Okay. So if we do that, of course, it'll be 2 with the remainder of 1. And then 2 goes into 17 8 times, the remainder of 1. 2 goes into 18 9 times, remainder of 0. And 2 goes into 0 0 times. So we have this. Okay. Since when we add up all these digits here, the 3, the 7, and the 8, we get 18. We know that 18 is divisible by 3. So therefore, we know that 3,780 will also be divisible by 3. But again, we can kind of do the same thing here by just saying, all right, we know that we have a 3 here. So if we use this 3, then we just multiply every other prime number that we have left to figure out what that's going to be here. Okay. And then we could move on and say, all right, well, I want to know what 4 times this is going to be. So you can just say, all right, well, we're going to use these 2 numbers. And then after that, everything else that's prime, you multiply that together and figure out what 4 times whatever it is to be 3,780. And then you repeat the process with 5. Okay. So let's say here, we just want to know, we just use 5. And then, of course, we use everything else to figure out 5 times what is going to be 3,780. So when I actually made that list, that was the process that I did. It did take a while because it was a relatively large number, but it is possible to do. All right, so let's go ahead and try some of these via factor by grouping. So for this first one here, I'm going to multiply first and last together. So we know that 3 times a negative 2 is a negative 6. And so the factors for that, 1 times 6, 2 times 3. And of course, we know that plus or minus would be with each of these. And once we're done, we're going to stick x's by each of these to rewrite this middle term. All right, so if we look, we know that 2 and 3 have a difference of 1. So the factors that we could use would be a negative 3 and a positive 2. Okay, because a negative 3 and a positive 2 here would give us the negative 6 that we're looking for. But also, if we add these together, we get the negative 1 that we're looking for. And just to put it in context of this particular example here, if we put x's here, then that would be this. And put x's here, that would be that, which is that. So now we come and say 3x squared, and in place of a negative x, we're going to write a negative 3 plus 2x, and then minus 2. Okay. Now, from this point, I'm going to group here and group here. Okay. So here I would normally take this sign right here and do plus a negative, but since I already have it grouped inside and it's not really messing with anything, I'm just going to leave it that way. The only time I would really want to do that is, let's say if we were doing this the other way. So let's say you wrote it as 2x minus 3x here, minus 2. And then from this point, if we were to group like that, then it may be advantageous to do the plus a negative number like that. Okay. So, but here, the way that I have it right now, I am just going to leave it this way and not change the signs. All right, so now that we have that, we're going to take the greatest common factor out of each group here. So the greatest common factor out of 3x squared and 3x is just going to be 3x. So if we do that, that leaves us with x in the first term, and this will leave us with an understood 1 in the second term, okay? Plus, and for the second group, we have 2x minus 2. The greatest common factor for those is a 2, so we're left with x in the first term and a minus 1 in the second term. Now, some of you may be wondering, well, how did you actually see that? And what I'm going to do here, once I've done erasing some of this other stuff here, is go through that so you can see exactly how we come up with factoring that out. So let's come over here and say 3x squared minus 3x, okay? If I actually write this out and factor everything totally, this will be 3 times x minus 3 times x. And so if you notice here, both terms have in common a 3 and both terms have in common an x. So that's why I'm factoring out a 3x here. Now, if you notice, for the second term, we have 3 times x, right? If we take that out, it appears to be nothing left. But one of the things that we know is that here, 3x times 1 is still 3x. So here we could look at this as having an understood times 1 that's there. And so when we do that, when we take out the 3x, what's left in the first term is just x minus, and what's left in the second term is a 1, okay? So that's how we end up getting over here 3x times x minus 1, okay? And we do the same thing here for the 2x minus 2. So I hope for those of you that may have had questions on that, that's how that gets cleared up. All right, so we'll get rid of this and finish up our problem. So for here, now that we see that we have in common x minus 1, if we pull out x minus 1, or factor it out rather, then what we have left in the first term is a positive 3x, and in the second term, a plus 2. And so that is how we would factor out this particular expression via factor by grouping. All right, so please note that we could have done the same thing by trial and error method, but I'm just using the factor by grouping method here to showcase. All right, so for the next example, I'll go ahead and do the same thing. We'll multiply first and last coefficients. We will get a 36. And so now we think about what times what multiplies to be 36, but adds to be 13. And so if we list these factors, 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6, we see that the 4 and the 9 works, okay? And so here we could say 6x squared plus, and instead of saying 13x, now we're going to say 4x plus 9x, and then plus 6. So we're replacing this one term here with these two. And then from there, we are going to group 2 and 2, and then we will factor out the greatest common factor for both. So for 6x squared, we know that this could be written as 3x times 2x. And of course, let me get rid of that here. Plus, and then 4x could be written as 2 times 2x. For the next one, 9x could be written as 3x times 3. And 6 could be written as 3 times 2. And so from that, you'll see that we have in common here 2x in both terms. So we'll factor out a 2x. What's left is 3x plus 2. And then for the second group, you see that we have in common a 3. Okay, so if we factor out the 3, so we have in common the 3's here, we have 3x plus 2. So now from there, we see that each term has a factor of 3x plus 2 in common. So we factor that out, and we see what's left is 2x in the first term and plus 3 in the second term. So we see that our final answer here will just be 3x plus 2 times 2x plus 3. Moving on to the next example here. We have 9x squared plus 3x minus 2. We'll do the same thing, multiply first and last coefficient. We get a negative 18. And so we want to figure out what times what is negative 18, but also adds up to be a positive 3x. And so if you're running through the factors of 18, you'll see that 6 times 3 is 18. But if we wanted to make it negative, one of the terms would have to be negative, one would have to be positive. So if we made the 3 negative and the 6 positive, this would work. Because positive 6 times a negative 3 is a negative 18, but 6 minus 3 gives us a positive 3. So now we take 9x squared and rewrite plus 3x as, and I'm going to do it this way, a minus 3x plus 6x, and then minus 2. Okay, so if I do it that way, then I can group and don't have to worry about changing the subtraction signs to plus and negative. All right, so from here, I know that 9x squared could be written as 3x times 3x, and 3x could just be 3x times 1. Plus, second term, we know that 6x could be written as 2 times 3x, and that 2 could be written as 2 times 1. And so from that, you see that we have a common factor of 3x in the first group here. So we factor that out, and we just have 3x minus 1 left. And then for the next one, we have a common factor of 2. So we factor that out, and we have 3x minus 1 left from there. And so from here, we see that we have a common factor now in both terms of 3x minus 1. So we factor that out. And what is left is 3x in the first term and plus 2 in the second term. And so this would end up being our answer, 3x minus 1 times 3x plus 2. All right. So now we move on and we say, all right, well, we notice that we can do this by factor by grouping, but we could also do trial and error method for the same kind of situation. And so again, when we do this, the caveat is that we have to try out a lot more things if we don't pick the right thing the first time. Okay. So just an example to kind of show you what I mean. So we start off by factoring 15b squared plus 26b minus 21. Notice that the first thing that we have to do is figure out all the factors of the first coefficient, which is 15, and the last one. And so from there, what we have to do is set up our signage when we factor. So we have plus minus as our signage here. So here and here, oops, here and here rather. So we know that we're going to have one with plus, one with minus, and we know we're going to have x's here. But now we have 4 spots to fill out instead of 2. And so if you notice down here in this area, I have to first figure out, all right, well, what am I going to put in the slots for the numbers next to the X, okay? And then after that, I have to try out all my factors for these two spots here. So I have to take each set and then try it out with everything. And if that doesn't work, then I have to take the numbers that are next to the X, either switch them around or use something different, and then try it all over again, okay? So as you see, what I've done is I've elected to say, I know that 3 times 5 is 15. So what I want to do is, let's put a 3 here, let's put a 5 there. And then I'm going to try 7 and 3 first, because I know 7 times 3 is 21. And then after that, I'll try 1 times 21 and see what that gives me, okay? So if I do 3 times 7, of course, I want the number in the middle to be positive. So that means that the bigger number is going to have to be next to the plus sign. So I would do this. And I'll try that out to see if it works, okay? So I'm going to erase some of this and show you what we end up getting. So if we try this out, then that means that our middle number here should add up to be a positive 26. So if we do 3x times a negative 3, that is a negative 9. And then we do the inner, that'll be plus 35, okay? And so if we look at that, we know that negative 9 plus 35 ends up giving us a positive 26. So that actually ends up working for us, okay? Now, imagine if I would have tried the 1 and the 21 first. Of course, that wouldn't have worked, okay? But again, part of this is just kind of having a feel for the numbers, and part of it is being lucky, okay? So it seems like it actually worked out for me there. So here, if you notice, what I actually did when I wrote this out is I tried the 3 here and the 7 there, okay? And one thing I think I just noticed here is that instead of having X's here, I should have B's. So I want to put a B here and a B there, okay? So I do apologize about that particular typo. So that should be a B right there, okay? All right, so coming back here, if I would have tried to put the 3 in the first spot and the 7 in the other slot, then you would have saw when I multiplied everything out, I would have got a negative 6b. And of course, negative 6b isn't the same as a positive 26b. So that's why I say with the trial and error method, whenever you have a coefficient, a leading coefficient is not equal to 1, sometimes you have some situations where you may have to do multiple iterations of trying everything out. Of course, this is what we actually did up here. And so we used the fact that we knew that the bigger factor had to be positive to try to place this in the right spot, okay? All right, and so we're back to this problem again. If you notice, this was the problem that we did via factor by grouping. And of course, it looks a whole lot shorter now, right? And so the reason that we know that is because for one thing, we kind of have an idea of what the answer is. But if you notice, for the coefficients that's next to x, we have a 6 and a 9 that's here. And of course, we also have 7 and a 10. And so the reason whenever we have these, if these numbers are relatively close to one another, okay, one of the things that I normally do as a rule is I try the factors that are closest together first. So here we know that 6 and 9 are closest together, and we know that 7 and 10 are closest together. Okay, so if all these numbers are relatively close together, then I try the ones that are closest together first, try to mix and match those, and then after that, I move on further away. Now, if you had a situation where this number was way larger than the others, so let's say if this number was, not to say this would work, but let's say if this number, instead of 123x, you would have 1230x, okay? Then from that point, I would start here at the factors that are further apart and then try to work my way back, okay? So that was one of the reasons why I knew to use 6 and 9 for the coefficients here and here, and then 7 and 10 for that, just as a first try. Okay. All right, so now let's do some of these on our own. So here, if we start off, we know that we have plus and minus because we have minus minus here. Our 3w squared, we know that that could be broken down to 3w times w. And so now we're just trying to figure out what are going to be the factors of 13, okay? So we know 13 is prime, so we're only going to have 1 and 13. Since this number here is kind of big, and we want it to be negative, we know that the 13 needs to be, the larger number is the one that needs to be negative, okay? So we'll put the 13 here, the 1 there. To check out everything, we'll go ahead and do that. The outer and the inner part of the FOIL method. So 3w times a negative 13 is a negative 39w plus a 1w, which gives us a negative 38w. So we know that this works out, and our answer is just 3w plus 1 times w minus 13. For our next example, here we know that our signage has to be, one has to be plus, one has to be minus, okay? And so now we have to figure out where we're going to put in the first terms of each binomial and then the second terms. So if we look at all the factors of 6, we know we have 1 times 6 and 2 times 3. So I'm going to use the factors that are closest together. So I'll say this would be 2x, that would be 3x. And then after that, I know that the factors of 35 are 1 times 35 and 5 times 7. So I'm just going to use 5 and 7. Since this number in the middle, this middle coefficient here has to be positive, I'm going to allow my 7 to be positive and my 5 be negative. Okay. And so if I do that, 7 is positive, 5 is negative. I'm going to try this out and see if it works. If it doesn't, then I'm going to switch the place of the 5 and the 7. And if that doesn't work, then I'll have to switch again. So here, if I go ahead and multiply this out, I'll have a negative 10x plus 21x, and this will give me a positive 11x, which is exactly what I want here, okay? So got lucky here and it actually worked out. So my final answer is indeed 2x plus 7 times 3x minus 5. Okay. All right, moving on to the last example here for this set. We have 4a squared b squared minus 4abw times w squared, okay? So in this case, you notice we don't have any numbers, but one of the things that we do know is we have signage, okay? And one of the things that we know here is that we're going to have minus and minus here since we have minus plus. We also know that whenever we try to factor out 4a squared b squared, that the 4, the a, the 4, the a squared, and the b squared are all perfect squares. Okay, meaning that we know that 4 is 2 times 2, a is a times a, and b is b times b. So here, if we arrange this, we know that we have 2ab times 2ab, and that will give us the 4a squared. So we have 2ab here, 2ab there. Now, we also know that for our last term, that w squared is just w times w. And so we don't have much else to go by here. So we'll just put a w here and a w there. And we'll check our outer and inner terms to see does this work. So we have 2ab times a negative w, which is a negative 2abw. And then with that, we have a negative w times 2ab, which is again minus 2abw. And negative 2abw minus 2abw is a 4abw, which is exactly what we need right here. So got lucky here. So therefore, our final answer is 2ab minus w quantity squared, since we're multiplying the same thing times itself twice. Okay. All right, so moving on. We have some special methods of factoring here. We're going to talk about the square root method first. And so the square root method first basically says if we do not have a middle term here, so in other words, this middle term was gone and our leading coefficient was a 1 right here, then we would just have a situation where we have x squared plus c, okay? And if it turns out that this value for c is negative, if it looks like this, then we have a situation here where we have the difference of two squares, okay? And so the easy way for us to look at this is that anytime we have x squared minus a number, whether it is a perfect square or not, we can always figure out what it's going to factor into by just saying x plus square root of whatever number's here times x minus square root of whatever number's there, okay? So, and here we are assuming that p is greater than or equal to 0 only because we know we cannot take the square root of a negative number. So some examples. Here we see that if we have x squared minus 25, then our p is understood to be 25, and thus square root of 25 is 5. So using this formula of x plus square root of p times x minus square root of p, our answer just ends up being x plus 5 times x minus 5, okay? So this is the situation or the example where the number p that you have here is actually a perfect square, okay? Now, for example B, notice that 7 is a prime number, and thus 7 will not be a perfect square, okay? So here, if we take the square root of 7, that's just going to be square root of 7. But similarly, just like how we did example A, if square root of 7 is the number, then that we multiply times itself twice to get 7, then we just do x plus that number times x minus that number. So you see it gets to be pretty easy to do. And my point here is that here we could rewrite this as x squared minus square root of 7 quantity squared, okay? And so that'll let us know what to use for p there. In the case of x squared minus 24, 24 is neither a perfect square or a situation where if we took the square root of it, it would just be some single irrational number, even though it is irrational. My point here is that if you notice, when we do the square root of 24, we have to break this down since we know that 4 times 6 is 24, that we can break this down as square root of 4 times square root of 6, and square root of 4 is just 2. And so now this would be what square root of 24 would be in its most simplified form. And thus, if we wanted to factor that, it would be x plus 2 times square root of 6 times x minus 2 times square root of 6. That'll pretty much be the same. All right, so moving on here. One of the things that we want to make sure of is that if we have an expression of the form x squared plus p, where p is greater than 0, then this particular expression is considered to be what we call prime, meaning that the expression is not factored. Okay. Now, if we went deeper, we would find out that this particular expression, if we tried to factor it, would have complex numbers in it when we factor it, but that's out of the scope of what we're trying to do now. Okay. All right, so let's finish up with some of these examples here. So if we start off wanting to factor x squared minus 4, we know that square root of 4 is just 2. So this would just factor to x plus 2 times x minus 2. For our next example, we just have 2 here. So square root of 2 is an irrational number, so it's just square root of 2. So we just factor this to x minus square root of 2 times x plus square root of 2. And we just leave it like that. For the next example, we know if we do square root of 8, that could be broken down to square root of 4 times 2. And per our nth root rules, we can say this is square root of 4 times square root of 2. And square root of 4 is just 2. So that simplifies to 2 square root of 2. So here, when we factor this, this will be x plus 2 square root of 2 times x minus 2 square root of 2. Okay. And that pretty much sums those 3 examples up. Have one more here with 28. If we do square root of 28, that will be the same as square root of 7 times 4, which here, if we did that, that will be square root of 7 times square root of 4, and square root of 4 is just 2. So if we rewrite that, that would just be 2 times square root of 7. So when we factor this out, this will be x plus 2 times square root of 7 times x minus 2 times square root of 7. All right. Now, the last thing that we're going to talk about here is the other special factoring forms. And so we have what's called the difference of 2 squares. Okay. Remember that the sum of 2 squares, we actually saw this a little bit earlier in the form of something like this. The sum of 2 squares is going to be prime. Okay. So we're not going to be able to factor that, but the difference of 2 squares, we can always factor to a plus b times a minus b. If we have the same expression being multiplied times itself twice, we could always multiply it out to this. And so the way that I think about this is that if I take this, I'll say a squared plus 2 times, so 2 times for second term, first term, so that would be that, and then plus exponent with the b squared. So that's sort of how I remember that. And so if we're doing the one down here, a minus b quantity squared, The only thing that changes here is the subtraction sign. So it's still a squared plus 2 times a times negative b plus b squared. Okay. If we roll down here now, we'll see that we have what's called the difference of two cubes and the sum of two cubes. Okay. And so with the difference of two cubes, if you have a minus here, it's different, same, same. In other words, minus plus plus. And then if you have a plus here, then you have alternating signs there. So you have plus, minus, plus there. And note that this factor here, the a squared plus ab plus b squared, or the a squared minus ab plus b squared, those factors are what we call that they cannot be broken down anymore. So they're irreducible factors. Okay, so irreducible factors. Okay, that's what this is, what that is. Okay, so using that, we're going to see some examples here and then try some on our own, and then that'll wrap up the video. So we have x cubed minus 64. And so if you notice here that 64 is 4 times 4 times 4, so that would be just 4 cubed. So in that, we could rewrite x cubed minus 64 is x cubed minus 4 raised to the power of 3. And so if we do that, then using what we know here about, let me erase that. So using what we know, a cubed minus b cubed, that will be a minus b times a squared plus ab plus b squared. Okay, and so where our b here is going to be 4. Okay, so that's why I have that there. And so then from there, everywhere where we have an a, we put an x, and everywhere where we have a b, we put a 4. And so that will end up with this expression here. And then if we just simplify by making 4 squared 16, we end up with this answer. Okay. All right, so for example 2, we've already seen this question before. We did this whenever we were talking about factoring via trial and error. But you'll also see that we can actually do this another way. If you notice, and this is the note that I have down here, is that if we look at the anatomy of what's going on here, if we let a be x and b squared equal 4 and 2ab equal 4x, then what all this comes out to be here is we see that this x squared plus 4x plus 4 sort of fits the anatomy of this particular special factoring. Okay, and to be very specific, I'll go ahead and write out and show you exactly what it is here. So here this would be x squared plus 2 times 2x plus 2 squared. Okay, get rid of all that. So, and if you notice here, this sort of fits the profile. If x is equal to a and b is equal to 2, then this is more like a squared plus 2ab plus b squared. Okay. So that's all I'm really trying to say down here, is that this x squared plus 4x plus 4 really kind of looks more so like the a plus b squared, where a squared plus 2ab plus b squared is in the same form. Okay. All right. So for the last one, we have the sum of two cubes. And so we notice that 125 is 5 times 5 times 5. So if we keep this, let me go ahead and erase some of this to make some room. So if we keep this in the form that we need it, we know that a cubed plus b cubed is going to be a plus b times a squared minus b squared plus, sorry, a squared minus ab plus b squared. Okay, and let me write that a little better. Okay, get rid of that. All right, so here we know that our a is going to be equal to x here, and our b is going to equal to 5. And so if we take that and just substitute everything into our equation here, this is what we end up getting. Okay, and then after that, of course, the 5 squared, we just simplify that to 25, and that is our answer. All right, so we're going to go ahead and move on and try some of these, and then after that, this will wrap it up. So here we know that we have the difference of two squares because we know square root of 16 is 4. So here this will just factor to x minus 4 times x plus 4, okay? Because we know a squared minus b squared, so in other words, this could be rewritten this way, is just a minus b times a plus b, okay? For this next one here, we know that 64 is 8 squared, and we have a squared there. 91 is 9 squared, so all this is just 8a quantity squared minus 9b quantity squared. Okay, so if we wanted to factor that out, this again looks like the difference of two squares. So we would have 8a plus 9b times 8a minus 9b. Okay, because again, this looks like two separate things that are being squared. So this fits this profile. For our next example, if you notice here, 9t squared will just be 3t times 3t. 30t is going to be 2 times 15t. And then, of course, 25 would be 5 squared. Okay. And so here, if you notice, we have 2 times 15, but 15, if we write that out some more, is going to be 3 times 5. Okay. So looking at that, we see that we essentially have 3t quantity squared 2 times, if we move the 3 here and the t together, we'll have 3t times 5, and then of course have 5 squared there. I'll go ahead and put parentheses around it. Then if you notice, this sort of fits the profile of, go back, sorry about that. This will fit the profile of a squared plus 2ab plus b squared, where in this case the a is going to be 3t and the b is going to be 5. And so since that fits that, we know that this is just going to be A plus B quantity squared. So all this just ends up being A, which is 3t, plus B here, which is 5 quantity squared. Okay. For the next example, here, this may not be obvious to you because you may want to do this via trial and error method, but to try to keep in with the rules that we're talking about here, this would just be x squared minus, if we do this, this would be 2 times 10 times 2x, and of course 100 will be 10 squared. Okay, so looking at this, we see here that we have this 10 here, so we can consider that to be a B, and we can consider the 2 to be the A here. So if we rewrite this, this will be 2 times 2x, and then this will be 10 right there. Do it like that. And so from there, if we try to use the ax squared plus, oops, wrote that wrong. So let's just try that again. This will be a squared minus 2ab plus b squared. So this is what we're trying to fit this into here. Okay. I'm not sure if that's going to work like that, but we'll see it, and if not, we'll change it up and do what we need to do. Okay. So right now I'm trying to call the 10 the B, and we're going to try to use, oh, okay, yeah, I see where my error is. So here, 20 is just 2 times 10, so we need to get rid of that 2 there. Right, so this should be more like this. Let me erase it. So here we have 2 times, just 10 times x here. That should be more of what it should be like. Now I'll just write all this again. Yeah, I'll just write it all over. 10 times x here. Okay, this will be 10 times x there. And so now, this all seems to make a little bit more sense now. Okay. So of course, we can use our value for, well, not value, but A will be represented by x, 10, B will be represented by 10. And so if we do that, that'll sort of fit this whole profile up here. So therefore, this ends up being, if we factor this out, we know that this is A minus B quantity squared. So A is x, B is 10, and of course that's quantity squared. Okay. So again, I do realize that you can do this via trial and error method, but I wanted to make sure that you saw how we could do this also the other way. All right, so we have these two final examples here, and then that will wrap it up for us. So in this case here, this looks like we're going to be using the difference of two cubes. Okay, so if we do this, this will look like a minus b times a squared plus ab plus b squared. Okay, and we're going to see if we can actually get this to fit. So we know 8 is 4 times 2, which is 2 times 2 times 2. So that's 3 2's. So we could rewrite this as 3 cubed times a cubed. And then 27 is 9 times 3, which is the same as 3 times 3 times another 3. So that will be 3 3's multiplied times itself. Okay, so this definitely looks like this is going to fit the profile here of the difference of two cubes. We know that 2 cubed times a cubed is just 2a quantity cubed via exponential rules. And thus this would be 3b quantity cubed. Okay, so following the rules that we have here, 2a is going to be in the first term, and was going to represent what a is here, and 3b is going to represent what the second term is there. So when we do that, this will just be 2a minus 3b, and then we will have 2a quantity squared plus, and now we'll say a times b, which is in this case 2a times 3b, and then we'll say plus b squared. In this case, that would be a 3b quantity squared. Okay, and then from that point, we just simplify. So we have 2a minus 3b. 2a quantity squared is 4a squared. 2a times 3b is 6ab, and 3b squared is 9b squared. Okay, and so that is what that would factor out to be. All right, so for our last example here, 64 is the same as 4 cubed, and 125, we've seen that before, is the same as 5 cubed. So if we rewrote this, this would look like 4x quantity cubed plus 5 quantity cubed. And so in that, we'll use the sum of two cubes, which is a plus b times a squared minus ab plus b squared. And so therefore, in using that, we would say that this is going to be 4x plus 5 times a 4x quantity squared minus 4x times 5, 4x times 5, and then that will be, oops, move that back up here. And so that will be a plus b squared, of course, which will just be 5 squared there. Okay, and if we kept on writing everything, 4x quantity squared is 16x squared minus 4x times 5 is 20x, and then 5 squared is just 25. And that would be what our final answer is. And so with that, this wraps up this particular video on factoring. I know this was a very long video, but I wanted to make sure that I got everything in so that you see every kind of example possible. And so hopefully this will be beneficial to you and help you out in your mathematical studies. And again, thank you for tuning in to Empowered Learning.